Okay, in Module 5 we want to add to Module 4 and we want to look at this idea of optimization. And so in Module 4, remember that what we did was, generally speaking, I guess, if we have a couple of quantities x and y that we want to work with and model about, in Module 4 that was amounts of two types of fertilizer, tomato and sweet corn. Generally speaking, with these linear inequalities, we can build these feasible areas, and I'll just sort of draw some generic feasible area like this. Could be my house after a high wind, but that's everything that's feasible as far as my x's and y amounts. And so that's what we ended up with in Module 4. And now, part of Module 4, then, we looked at adding ideas of feasibility, like, oh, well, suppose we want to ask what amounts of x and y we could make, and in that case, we looked at something like x plus y, because x was the amount of x and y is the amount of y, whatever it was. In our case, again, x was the amount of tomato fertilizer made, and y was the amount of sweet corn fertilizer made. And so this was our total amount, and we let that equal various numbers, and that plotted as lines like this, depending on what that number was. So equals, and so for instance we used 50 and 100 and so forth, and we got these lines. Well, so if you look at that pattern in those lines, which you were asked to do in that module, what we notice is if I just call that amount z, so z could have been 50 or 51 or 100 or 101, something like that. What we noticed was as z went up, we went out this direction. So z is increasing. And so as we do that, we could ask, well, what's the most I could make? And we could try different values of z, and that's what we'll do in this module. We'll use a slider in Desmos to make our job slightly easier. But we increase z, we get this family of parallel lines like this, and actually what we end up looking for is sort of that last one. The last one that actually touches the feasible region. Okay, so this one touched right at that corner, and so it still has some values that are feasible, but if we increase z in this picture by moving these out like this, then this value here, this z that makes that line, is our optimal z. So right here, what we would call that point often is something like x star, y star, right? They're stars because they're special, they have the maximum amounts there. And then if we add those two things together, x star plus y star, what we would call that is z star, or our, in this case, maximum z. And so what you'll do in the first part of the guided project is you will look for what that value is. What's that maximum value that I can increase this total amount, x plus y, to, and still stay just barely in the feasible region. Okay, and it'll look pretty much like that when you do it. Now let's look at some possibilities of things that could happen. For instance, that first one, I'm going to not color things in as much and kind of make things pretty simple here. So here's my feasible region, I'll call it F. And suppose I want to maximize. Typically when I maximize, I'm going to be drawing lines out this direction. Now, as you look at this, all of a sudden it matters a lot sort of what this equation is, the x plus y, because the x plus y equals some number. I could solve that. So, over here, say I've got x plus y equals, and we'll just say 200 for the heck of it. I could solve for y, and I get y equals minus x plus 200. So you see that's definitely a straight line, but I can see the slope, it's -1 and so forth. And so in this particular picture, maybe this is my x plus y equals 200, and it hits right there. But you see the slope of the line has a lot to do with where it's going to hit on this feasible region, because if I made the slope more negative, now more negative would be like y equals negative 3x plus 200, something like that. And so consider if I had like 3x plus y equals, and now it probably won't be 200, but my grandfather always said don't wreck a good story with facts, so we'll just say 200. Because it's got that steeper slope, what might happen is it might come through this way. So there's my line, 3x plus y equals 200. And so you see, if for whatever reason this was my objective, I'm not sure why that's moving around like that. If this was my objective, whatever that means, I don't know why I would have 3x plus y. In our module, we have something like 4x plus 12y. I know why that is. That had to do with revenue. But let's just say if I had 3x plus y as opposed to x plus y, when I increase this number out here, I might hit in different spots. And so that's what we're looking at is actually I'm always, because everything's straight lines, I will always hit at a corner. So that's something to realize, is I will always hit at one of these corners. If I'm not hitting at a corner, I'm really not looking at this correctly. Because again, you do it yourself. Try to draw, any old picture with straight lines, and then use another straight line and put it either as far out or as close in as you can. And so for instance, if I had that straight line and I looked at parallels to it, then I'm either right here or I'm right there. If I take the farthest out I could go or the farthest down I could go, I hit at a corner. The only exception is that actually you could hit at two corners, because suppose my line that I'm trying to maximize or minimize, in our case we're only trying to maximize, so let's send it out this way. If it is parallel to one of the constraint lines, one of the edges of my feasible region, I'll actually hit two corners and everything in between. So it is possible to not hit a corner and be at your best answer. Now, I have to be careful, or we all have to be careful what I mean by that. Because I said, well, not hit a corner. Well, that's not really true. I hit that corner and I hit that corner. So really I don't have to hit only a single corner. I could hit two corners and the whole edge there, that whole line of the feasible region. So that could happen, in which case, what I might want to do is keep track of that corner and that corner, because that would tell me kind of what my x's and y's could range between. So here's my x, there's my y, here's my x, there's my y. And so that's all we're doing with this optimization. We are starting with some feasible region. Okay, and again, I can draw it with any straight lines I want. We had a particular feasible region from Module 4. So we're starting with that particular feasible region. And then we're going to try maximizing a couple different things. We're going to maximize our total amount. Okay, so we're going to use this x plus y equals z. And we're also then going to ask a different question. Well, let's maximize our revenue because we looked at that in Module 4. We asked, well, if we sold this fertilizer, what could we sell it for? And I think, I'm not looking at it right at this moment, but I think that was 4x plus 12y equals z. And so what happens in these two is if I were to solve for y, I would see that, for instance, the x plus y would have this slope of -1. That looks like about a slope of -1. So that's, we're going to be doing something like that. But with this one then, if I solve for y, I'll actually get a slope of -1/3. So, it'll be, more like something like this, and that's that function. But we're going to push both of them out as far as we can. Now I drew this one right at a corner. It looks like with this picture I drew, if I pulled this out, it would be at that same corner. Okay, but it doesn't have to be. Again, looking back at these things, you can have different possibilities. You could have that corner for one and that corner for another, and it could even be that you hit two corners with one or both of them. But that's what we're doing. We're going to maximize this equation. We're going to maximize that equation. We're going to get those two different answers for that, and you're going to write it up. But that's the concept we're trying to get with this idea of optimization. Okay, so we'll call that good for this video, and I'll probably do one other short one.